Hello, and welcome to this lecture. What we will do today will be to talk about vibration of shafts. As we know, the shaft as it rotates, it is not perfectly centered along the axis, and if we have any deviation from complete symmetry, a shaft can oscillate and induce dangerous vibrations. Not only that, but if we have masses attached to the shaft, such as gears and pulleys and other devices, then you will have concentrated masses, nearly concentrated masses, that can also induce unnecessary vibrations. So the subject is that we would like to find the types of vibrations, or we want to characterize them with the rotational speed at which you get significant oscillations. And what we will see is that we'll discover that at a certain speed of rotation, RPM, the shaft can go under very heavy oscillations, and this is referred to as the critical shaft speed. And then as you increase the speed of the shaft, then it goes into another mode of oscillations, and a third and a fourth and so forth. So you have various modes of oscillations, but the most dangerous and most critical is the first mode. So that's what we will discuss today, and what we wanted to do is look at the following situation. What we want to do is that we want to have discuss a shaft, and this shaft will have, let's say, a rotation at an angular speed omega, and it is simply supported at some locations, like those locations here, but it will oscillate up and down. So this is case number one, which is free vibrations of a shaft without any attached devices. And then case number two that we will study is the same shaft, but now we're going to look at the possibility of having different masses or different gears, and the gears can induce forces F1 and F2 on the shaft as it rotates, and therefore we are looking at what is the situation with this shaft, and here we will look at attached masses as well. So these are the two general cases that we will study, and what we will see is that we have about two levels of analysis. The first one is going to be deriving a simple equation for the critical speed of a shaft without any attached masses. And then we will look at two other methods for deriving the critical oscillations or critical vibration speed for a shaft with attached masses. So the procedure that we will follow will be like this. We will have number one is a critical speed of a free shaft. And in this case, we will find the critical speed, we will derive it. And then number two, when we have attached masses or distributed masses, then we will go into two methods. One method is called the Dunkerley equation, and the other one is based on an approximation by Rayleigh. So we will derive Dunkerley, and then we will use Rayleigh to compare. So let's start with the first idea. And the first idea here is that I have a shaft, and the shaft is under distributed forces, and the distributed load, let's say if we have a distributed load here, a load per unit length is Q, and this will be the force per unit length. And we know from our background that if we have statics in statics, the load per unit length is balanced by the elastic energy in the beam, which is E times I times d4y by dx to the power 4, where y is the vertical deflection. Now, if there is an imbalance between these two forces, then we can imagine that we have an effective force, which is Q minus EI times d4y by dx to the power 4. This imbalanced force, if it is dynamic, then it should be equal to the mass times the acceleration. So in this case, the acceleration is d2y by dt squared. And we have now to switch from ordinary derivatives to partial derivatives because we have the time and the space on both sides. So this is kind of the basic equation that we have to solve for shaft vibration. And as I mentioned in this course, we just wanted to know where things are coming from, and then we focus on the application for the design. So let's take a few minutes to figure out how we can derive the critical speed of vibration for a beam that is supported freely on both ends. So it's like a simple support where the deflection is 0 on both ends. And then we just move on directly to the other methods. So if I have now the beam is supported at x equals 0 and x equals L. And at these locations, y is equal to 0. And in both sides, vibrate, it will go up and down like a part of a sine curve. So in order for us to describe this motion, we're going to assume that y, which is a function of x and t in general, so it's a function of x and time, is composed of the real of a function of x alone times a function of time which is predetermined, which is e to the I omega t. As we know, e to the I omega t, it contains a sine and cosine by Euler's equation. And now we look for what is y hat of x. So if we take this and substitute back into this equation, all what's going to happen here is that the time, we know the y hat, but anything like if you take the derivative with respect to time twice, then you actually replace that with omega squared, because every time you take the derivative of e to the minus omega t, if you take d by dt, for example, here, then you get minus I omega times the same function, which is right here. You take another derivative, d by dt, of the same, then you get another minus I omega, and therefore this I squared, so you get minus omega squared times the same function. So in this case, when we substitute, we get we replace just the derivative with minus omega squared. So when we substitute, we get now only an equation of x, ei d4y hat, the function of x that we want to solve for, minus m times omega squared times y hat equals 0. So the time derivative disappeared by this substitution, and now we have just an equation as a function of x. And this equation can be satisfied if we just write y hat as equal to a sine or a cosine. The easiest way will be a sine function, like a constant times sine beta n times x, where beta n is obtained from here as m times omega squared over ei to the 1/4 power. So if we just take this, substitute it back here, we will find that this is the beta n for the solution. So if we know that y hat at x equals L is equal to 0, Then we substitute this A sine beta n times L. This should be equal to 0, and this is only possible if beta n times L is equal to 0, meaning that this is the critical condition for the solution of this equation. So that would be our condition that can determine omega, and omega is the radial, the RPM, or the how many radians per second at which you have the oscillation or the vibration. So if we just now say that for beta n times L, which would be like this, should be equal to 0, it means that the beta n times L should be equal to a multiple of pi. So if beta n times L is a multiple of pi, then sine of multiple pi will be equal to 0, and we satisfy this condition. And we can rearrange now and find the write the solution for this equation. I'm going to write it omega n as equal to n pi over L squared times the square root of EI over M. And this is now the final equation that we have derived, and this equation is the shaft, critical speed for the shaft. So that's kind of the simplest. I went through it a little bit quickly because we didn't want to cover too many different boundary conditions. It can give you some different answers. This will be for a boundary condition where we have a shaft that is simply supported on both ends. We can find now the critical speed of the shaft without having any masses attached to this shaft. So now we can move on and look at the other situations. And before we do that, this is the equation that we just made the derivations for. And if we usually substitute with the mass in terms of the weight, so the mass is equal to the weight divided by the gravitational constant, because the weight is equal to mg. And that's basically gives us a way, once we know the weight of the shaft and the cross-sectional area, because this is we'll be able to, it's per unit length, so the weight times the cross-sectional area will give us the mass if we divide it by g, because it is per unit length. So that's now a way to calculate the critical speed for the shaft. Let's call it omega s. This is for the shaft. Now, without proof, now we're going to move on to Rayleigh's method. And Rayleigh's method is for a case when we have lump masses. So if we have a shaft and then I have a weight here and a weight here and a weight here, this is W1, this is W2, W3, and each weight gives us a deflection. So there is a deflection Y1 here, deflection Y2, deflection Y3. These are all static weights and static deflections, which we know how to calculate now. If we have the weights and the deflections, then an approximate formula for the critical speed of a shaft with concentrated masses is that you take the sum of the weights times the deflections, multiplied by g, and divided by the sum of the weights times the deflection square, and then you take the square root. So we'll keep that in mind as we just move on to the final method that we have, which is Dunkerley's equation, which we will derive. So we have made now a derivation for the critical speed of a shaft that doesn't have any masses, and we stated the Rayleigh equation, which is an approximate equation if we have a bunch of masses. Now let's now assume that I have a continuous shaft and it has either its own mass, or you can have masses on top if you just segment it to different elements and derive the Dunkerley equation that we're going to use. So if you look here, you see the shaft is broken into different elements here, element 1, 2, 3, 4. Each one has its own mass, which we assume that it is kind of concentrated. And before we make the derivation, we have to consider the effect of a concentrated load at any given point, because the masses will be considered concentrated loads. So suppose that we have a unit load at any point here that is described by the position AJ and BJ from the two ends. So we know the length of the shaft is L, and the unit load is concentrated at distance A sub j and B sub j from both ends. So this is the unit load is a J. Now we want to compute the deflection at a point x sub I. So what is the deflection of due to a unit load at any point away from that unit load? So that's the idea of delta ij. Delta ij is the deflection at point I, which is right here, due to a load that is placed at point j, which is right here. So this problem, we know the solution for. We have a table for, or we can solve it analytically, but better yet, we can use the table where the delta ij is known. So it's you have an equation for xi less than ai, another equation for xi greater than ai. So these two equations here will give you the value of what's known as the influence coefficient. So to summarize here, the influence coefficient is the deflection at any point along the beam given that you have a unit load at some other point. So that's kind of the relationship between the two. And we know that value from these equations here, 724. So let's now move on to trying to have a simply supported shaft, and it has only 3 loads, but that can be generalized to many loads if we wish. So the deflection at point 1 is a result of force 1 that is located at point j equals 1, force 2 located at j equals 2, and force 3 located at j equals 3. And note that this is delta ij, so this is the effect, and this is the cause. So the cause is at point j, which is the load, and the effect is at point I, which is where we want to find the deflection, which is y1. So yi is either y1 or y2 or y3. This is I equals 1, 2, 3. So that's kind of the way we know now from the previous equation. We can figure out delta ij. Give me an I and a j, and I can plug them in here, and then I will find all of these influence coefficients. And you see now that I have kind of a matrix equation because I have 3 equations here. Each one describes the deflection at point 1 and 2 and 3, knowing the bunch of influence coefficients. In this case, we have 9 of them because we have 9 combinations 3 by 3, and knowing that we have some forces F1, F2, F3. Now for the special case where the forces are actually not arbitrary, but the forces result from centrifugal motion, then you can think of the deflection. If you have the shaft, initially the axis is like this, and then it deflected like that, and at any point the deflection is distance y, and then you have a mass here, m, and then the mass is rotating around the shaft. So the force is m times omega squared times the distance y1. That is actually the centrifugal force of that mass rotating about the axis of the shaft. So this is like taking a sling, and then rotating it like that, and you have a mass on the end of the sling, and the distance is the deflection y. So it's m times omega squared times y, will give us the centrifugal force. So in this special case, the centrifugal force is substituted for F1, F2, F3, and we have now a system of equations, y1 on the left, y2, y3, and on the right you have again y1, y2, and y3. So we can rearrange those. These are they turn out to be, instead of an inhomogeneous system, becomes a homogeneous system of algebraic equation. And the homogeneous system, as you know, is like it can be solved only if the determinant is equal to 0 of the coefficients. So you have a determinant that has this coefficient m1 delta 1 1 minus 1 over omega squared, and then another coefficient, a third coefficient. So if you set the determinant to be equal to 0 for this system, you will get a solution. And the solution can be satisfied by finding the value of omega. That's unknown. This is unknown. This is what should be known to solve this system of linear equations. And if we have three masses, then you will expand this. So you multiply the first term times this times that, and then you take any combinations for the determinant, like the sub determinants. And as we know from our algebra, when we expand the determinant, we get a cubic equation. So we have 1 over omega cubed here, 1 over omega squared, and we have other term 1 over omega squared without to the power 1. So we'll just continue, and then a constant term. So you have a determinant that you should solve in order for us to find the critical value omega that satisfies this equation. Without solving it, we can actually do something, and that is saying that the sum of the roots, as we know we have 3 roots, omega 1 and omega 2 and omega 3. These are the kind of the roots that we should find. We know now that the sum of the roots here times the quadratic term, or the quadratic term, whatever coefficient here, should be the sum of the roots. And it turned out to be that the coefficient of the quadratic term is m1 delta 1 1 plus m2 delta 2 2 plus m3 delta 3 3. And therefore, without solving a cubic equation, we equate the coefficient of the quadratic term to the sum of the 3 roots. So we don't know the exactly individual roots, but we just know now that the sum of the 3 roots is given by this equation 729. In order for us to proceed, we're going to define omega ii as the critical speed if we have mi is acting alone. So there's no other 2 and 3. In other words, if you cancel 2 and 3 and cancel 2 and 3, then you have 1 over omega 1 becomes, by definition, 1 over omega ii squared, and this will be equal to mi delta ii. So this is a way to rewrite. So this is redefining what is mi delta ii as a new quantity, just writing it as 1 over omega ii squared, as if we have just a mass, one single mass that is rotating. So when we do that, then the sum of the 3 roots is, we replace now the masses times the influence coefficient by the defined critical speeds if the masses act alone, and obtain this equation 730. Now, if we just now look at the situation here, so this is, in other words, this here is the idea, is that we have, in general, if we're just doing like math, we can just take this determinant equation to MATLAB, and then MATLAB can find the solution of the cubic polynomial, and it will give us omega 1, omega 2, and omega 3. That's the kind of the proper way, mathematical way to do it. And if you have more than 3 masses, then of course the determinant is going to increase but it's still solvable because you can solve it using, like, it's almost like it's an eigenvalue problem. Now, in the one observation that can be helpful is that the omega 1 is usually lower, much lower than omega 2, and the omega 2 is much lower than omega 3. So there's kind of a succession of critical speeds going from the first critical speed to the second to the third, and that succession can be used to our advantage so that we can simplify the solution of this polynomial. And therefore, if we know that omega 2 is larger and omega 3 is much larger, then this term is going to be negligible, this term is going to be negligible, and therefore we have a simplified, you see this dot here, means that approximate simplified way to find the first critical speed as the sum of 1 over omega 1 squared is the sum of 1 over omega I squared. So all what we have to do now in Dunkerl's equation is find omega II. So this is the task, and omega II, as you know, is defined as mi delta II. So it becomes omega II is equal to mi delta II. And that's basically what we need to do to put the concentrated loads and then find the influence coefficient, and then move on to approximate the solution to find the first critical speed. Now, just a little bit of elaboration is that if you consider we want omega 1 squared, for example, then we can write it as 1 over m1 delta 1, so there's no problem. We can find delta 1, and m1 is the weight divided by g, so this is no problem. But it may be kind of easier if we just imagine that we move the load to the center instead of at any arbitrary point, and redefine, we want to kind of redefine a new load at the center that would give us exactly the same vibrational speed. So the redefinition is that this is constant, this is the same, so we can write it as g divided by omega 1, or the w1 delta 1, and then we imagine we moved the w1 to the center, so we're going to write it omega 1c. This is the hypothetical equivalent force at the center, times delta cc, which is the we know the influence coefficient if the load were at the center, and therefore we have now an expression for defining the equivalent load at the center of the beam. In other words, now to summarize, we should just go directly, the easiest way is directly to use this, but if you want to use an approximation, as we'll see in one example, or a different method of calculation, then we can translate the loads to the center via this equation. So it's the ratio of the influence coefficients. Once we translate them, then we consider them all summed together at the center of the shaft. So with that, I think we have all of the methods that are needed, and we wanted to discuss an example. So in here, I'm going to discuss an example so we can apply the three different things that we learned, basically the critical speed of the shaft alone by the solution that we given for the deflection equation. And then second, we wanted to apply Rayleigh's method, which is an approximate method, find static deflections, weights, multiply them, and divide, and then get the answer. And then the third one is by Dunkerle, where we have an approximate expression for the first critical speed once we have the loads and influence coefficients. So here's the example 7.5. We have simply supported steel shaft, and the beam it has 1 inch diameter and 31-inch span between bearings, and it's carrying two gears. One is weighing 35 pounds and the other one is 55 pounds. First is find the influence coefficients. So let's go find the influence coefficients. Influence coefficients, in order for us to find them, we have to find the moment of area, and we have to find E times I multiplied by L, 6L. Then we get this number. And then the influence coefficients, just remind you, the influence coefficients for a shaft that has in here is given by delta ij from here. So you can see 6EIL, and then these are locations. B is a location, X is a location, L is the length of the shaft, and this location and location. So we have to now substitute into the equation to get the influence coefficients, and we'll do that immediately in the equation. So as you can see here, delta 1, 1, then this is the L, and this is the B and the X squared, and this is your 6EIL is right here. So you find that the influence coefficient delta 1, 1 is 2.06 times 10 to the minus 4 inch per pound force. It means that if you put 1 pound force at this point 1, because we have 3 points along the shaft, at the first point, then you get a deflection of 2.06 times 10 to the minus 4 inches. Doing the same for delta 2, 2 and delta 1, 2 and 2, 1, which are the same. That allows us to now calculate the total deflection y1 as the weight times its influence, the deflection, plus the second weight times its influence in here. Notice actually that we have two weights, and therefore we have the matrix deflection matrix is basically three numbers. So we have delta 1, 1, we have delta 1, 2, we have delta 2, 1, we have delta 2, 2, because we have only two weights. And therefore we can get y1 and we can get y2, which are the static deflections. So all of these are static. And why do we need static? Because we're going to use in a minute the approximate formula of Rayleigh, because we need to find the static deflections multiplying by the weights and in the numerator, and sum them multiplying by g, and then in the denominator we multiply them multiply the weights by the static deflection square and sum to get the critical speed. And that's basically what we will do. Is the next step is the sum of mi yi, and then the sum of mi yi squared, and we apply now Rayleigh's equation to get the critical speed, which is turned out to be almost 1200 RPM. So we keep that in mind as we just continue the solution. So let's go back and see what is required. We wanted to use now, we found the influence coefficients, and we wanted to use number D. We wanted to find the using Dunker's equation. We applied here to find omega, the first critical speed. So moving on, we have here 1 over omega 1, 1 squared is delta 1 times m, delta 1, 1 times m1, and m1 is w1 over g. So we can find omega 1, 1. This is the self critical speed for one single mass, like gear 1, and this for gear 2. And now we can use these self critical speeds, or self speeds rather, to estimate the first critical speed of the shaft using Dunker's equation. So 1 over omega 1 squared is the sum of 1 over omega ii squared. And doing that, we get a number for the first critical speed, which is 1149 RPM, which is somewhat smaller than what we obtained before. So we have obtained now the critical speed, two different methods. Let's go back and see what is required. We want to use the superposition to estimate the first critical speed, which we did. And then we want to, superposition is superimposition of the forces. Like we said, we're going to translate this force to the center. We're going to translate this force to the center by doing an equivalence transformation, and then estimate the first critical speed if the two forces were at the center. So that's what we will do here. As the translation, we have to find the delta CC center, where now B is at the center, X is at the center. So this is half of the shaft. The shaft length is 31, so half of it is 15.5. And therefore we get delta CC is 4.2 times 10 minus 4. And now I can translate the weights. So from W1, I ratioed by delta 11 over delta CC to get me W1C, which is a fictitious force at the center. And W2, I translated, I get a fictitious force at the center. This turned out to be 17.1, and this is 46.1. And therefore, you can actually use them to find the critical speed of the shaft, because the two forces are exactly in the center, and therefore you can add them up. And here we get another answer, 1150. That is also very small difference from before. The final requirement is that in addition to, we have found out that the critical speed of the shaft by itself should be estimated from the solution of this boundary value problem that we started at the beginning of this lecture. Now, what happens if you have the gears on them? We estimated that the critical speed is going to be somewhere between 1150 and 1200 RPM. Now, what happens if you just consider, in addition to the gears, you consider also the influence of the rotation of the shaft itself on the critical speed? Well, the solution is simple. We want to find the critical speed of the shaft by itself, and then treat it as if it is an additional mass to the system. And that's what we will do. So for the shaft by itself, it has an elastic modulus of 30 MSI. Its weight is given in pound force per inch cubed. And this is a cross-sectional area. So we apply the equation we derived earlier, very early in this lecture, for the shaft critical speed without any gears. And we find that it is very high, almost 5,000 RPM. So now we want to consider this as an additional mass and use Dunkerley's equation. So basically we add 1 over omega s squared to the right-hand side. So 1 over omega 1 squared used to be the sum of the two gears, 1 over omega 1 squared and omega 2 squared. And now we add to this the influence of this shaft as if it's it is a concentrated mass by itself. So the result is that omega 1 is 1120, which is less than what we computed before. In other words, if you consider the shaft to add some effect on the critical speed will kind of be reduced. If we didn't consider the shaft itself, then the critical speed will be high, on the order of 1150 to 1200 RPM. And with that, we've covered everything we wanted to know about the vibrations and the critical speed of rotating shafts with gears and other attachments.